Welcome everyone, Math 105. This is Lesson 15, Applications of Dimensional Analysis. Dimensional analysis is an incredibly powerful tool. It's not just used to convert units, it can be used to set up equations. If we have an equation, it's clear that the numbers on opposite sides of an equal sign have to be the same. But it's also true that the units have to be equal to each other as well. And we can use that to create equations for situations where we don't know the equation ahead of time. So I'm going to go through the procedure now for creating equations using dimensional analysis. So the first thing we need to do is take a look at the quantities involved and their units, and think about which mathematical operations are possible with those units. As it turns out, not all operations are going to be possible in all situations. If we have two quantities with the same units, then those quantities can be added or subtracted. But if they have different units, they can't be. Quantities with the same units can be multiplied, and in doing so, we create higher powers of that unit, an exponent. And quantities with different units can only be multiplied, divided, or taken to a power. So what we're going to do is we're going to set up equations with the possible operations involved, and then see if the units on one side of the equation equal the units on the other side. If they do, then we've got a valid equation. If they don't, then we need to try again. So I'm going to go through this procedure with example 1, and we've got three quantities there. We've got time in seconds, and that's what the question is asking for, so that's unknown. We're also given a distance in meters, 345.45 meters, and we're also given a rate, which is speed, 23.5 meters per second. And with these three quantities, we're going to set up an equation and see if it works. So I'm going to try out this equation first, t equals dr. I know I can multiply d and r together, that's no problem. Multiplication is never a problem. So let's see what happens to the units then. So on the left-hand side we have time, and time is measured in seconds. So I'm just going to write seconds on this side. You can abbreviate, I'm going to write it all out. And we're going to see if it equals the same thing when we multiply d and r. So d is meters, and we're multiplying that by r, which has units of meters per second. All right, now let's multiply these two together. Just like if we multiply 2 times 2, we can get 2 squared. If we multiply meters by meters, we get meters squared. So on the left, we still have seconds. And on the right, we have meters squared over seconds. Well, these two quantities don't equal each other. So that's not a valid equation. So we have to eliminate that one. Right? So this is going to require quite a bit of experimentation. And when you're working on your homework, what I recommend doing is having a scrap piece of paper next to you that you can just try things out on. So let's try a different equation. Instead of t equals dr, I'm going to try d equals rt. All right, let's do the unit analysis now. Distance on the left, meters. And on the right, we have r, which is in meters per second. And we're going to multiply that by t, which is in seconds. Now on the right, we've got seconds in the numerator and seconds in the denominator. As we saw when we did unit conversions, when that happens, you can cancel those units. So all we have on the right is meters. So that matches the meters that we have on the left. So that makes d equals rt a valid equation. And now we can use that to solve this problem. So plugging in the values then, we've got 345.45 for D, 23.5 for R. And then solving for t, divide both sides by 23.5. And that gives us a t of 14.7 seconds. Now for your turn number 1, take a look at the situation from example 1 and come up with a different equation that's valid. We're going to need to use a different operation other than multiplication. Just a reminder, when you're working on your turn, just pause the video, work on it, and restart when you are ready. Alright, so instead of multiplication, we can try to use division. So R equals D over T. So on the left we have R, which has units of meters per second. And on the right we have distance on top, which is measured in meters. And on the bottom we have seconds. So those match, and that's a valid equation. So if we want to find T, we can plug into that equation. So that gives us 23.5 equals 345.45 over T. Alright, now to solve, we use this swap trick. So swap T and 23.5. So we got T equals 345.45 over 23.5. Which when we're solving over here, that's exactly what we got. And so T equals 14.7 seconds from that equation as well. So there are going to be different ways you can set up the equation that will be valid and give you the right answer. Just make sure the units match on one side and the other. Alright, so try this technique out with your turn number 2. For walnuts, Super One Foods charges a price per pound of $7.49. Set up and solve an equation to find the total cost in dollars of a bag of walnuts with a weight of 3.78 pounds. So just be clear, the units on P, price per pound, are dollars per pound. Right? Dollars per pound. Now I recommend writing the quantities out like this so you have the units right in front of you, and it may be easier to see the relationship between the quantities then. And C is in dollars, W is in pounds. All right, so I'm going to try out a formula here. C equals PW. And let's see if this works. So on the left, our units are dollars. So I'm going to replace C with its units, dollars. Use a dollar sign for that. And on the right, we have P, which is dollars per pound. And then W is measured in pounds. All right, now pounds on top, pounds on the bottom, those will cancel, leaving us with dollars equals dollars. So the units match, so that is a valid equation. C equals PW. We can use that to solve this problem. I'm going to plug in what we know. We know P, which is 7.49. Once you start solving the equation, leave the units out. Don't want to include those, it can be confusing. And then W is 3.78. So multiplying those two together, we get the cost. And we get a cost of $28.31 for the walnuts. All right, next up, your turn number 3. Now it's gonna involve some vocabulary that may be unfamiliar. It's from chemistry, but you don't need to know what these words mean. You just have to do the analysis with the units. And that's very helpful when you encounter a new topic and there may be some unfamiliar terms. So we got a mole in chemistry is the number of atoms of an element or compound. The atomic weight, W, of chromium is 52 grams per mole. Look for those keywords like per. Set up and solve an equation to find the number of moles, N, of chromium in a sample with mass M of 197 grams. It's important with analysis problems like this to relax and take your time. Just don't expect these to be quick. Your turn number 3. All right, so I'm going to write out an equation. We'll see if it works. All right, W equals Mn. All right, we got for W, is 52.0. I'm going to use some abbreviations now. G for grams and MOL for mole. All right, then we've got N, unknown, the units of mole. And then we've got M, 197 grams. All right, let's see if this equation works. On the left, we have W, which is in grams per mole. On the right, we have M, which is grams, and N, which is mole. Okay, those two are clearly not equal. Here we have division, grams divided by moles. Here we have grams times mole, so that's not going to work. So get rid of that one. Try something else. All right, how about W equals M over N? All right, so grams per mole over here. And then we have mass on top, which is grams, and N on the bottom, which is mole. And they match. And this ends up being really a good technique for setting up an equation if you have a rate like this. All right, we already have division in the units. So on the other side of the equation, use division with the variables so that the units will match. So sometimes the operation on the units like this, where we have division, is going to give you a clue. And now we can plug in our values. All right, for W, we got 52.0 equals 197 for N and N on the bottom. All right, now we need to use a swap trick again, and then just keeps coming up over and over again. So this is a really useful trick. So make sure you've got this one down. So swap N and 52, N goes over here, 52 goes in the denominator. 197 divided by 52, and we get N equals 3.79. And the units on N are mole, and this is what we're talking about of chromium. 3.79 mole of chromium. Now, some formulas happens quite often in science and business, we've got units with exponents. That's right, units can have exponents too, not just numbers. Example, we're going to find the height of a box in inches, which has a width of 18 inches, a length of 12 inches, and a volume of 5,184 cubic inches. Height is unknown, measured in inches. And the length is in inches. Volume is in cubic inches. All right, now as I said in the introduction, if we have quantities with the same units, we can add or subtract them together. Well, let's try adding them. Let's try V equals H plus W plus L. All right, so on the left we got inches to the third power equals inches plus inches plus inches. Now when we add things together, the units don't change. You have 5 basketballs plus 3 basketballs. You don't get 8 basketballs squared. You just get 8 basketballs. So when we add these things, the units together, the units don't change. So what we end up with, inches to the third power equals inches. Well, that's clearly not true. This one's to the third power, this one's to the first power. So that doesn't work, and that means this equation does not work. Well, let's try a different operation then. Let's try multiplication. So V equals H, W, L. Oops. Units now. Inches to the third equals inches times inches times inches. So we've got a quantity multiplied 3 times. So that's to the third power. Inches to the third equals inches to the third. So there's our formula. Once you get a match, then you know you got the correct formula. So volume equals height times width times length. Now we can plug in the values. 5184 for the volume. And the height we don't know. Then we can do h times width is 18 and length is 12. All right, now let's multiply together. 18 times 12. So we can simplify on the right. So that's 216. So we get 216 on the right. Now we'll divide both sides by 216. And h is 24 inches. Your turn number 4. So some quantities don't have single units. They have units that are made up of a combination of single units. So we've seen these with rates. Speed, meters per second, miles per hour, something like that. And acceleration, a measure of how fast the velocity is changing. So a driver, if you're driving a car, you can feel the acceleration when you hit the gas pedal. And you see the speedometer changing. As speed changes, that's acceleration. The units for acceleration are meters per second squared. It's meters per second divided by seconds again. So that seconds ends up in the denominator, we get seconds squared in the denominator. You've got a vehicle starting from rest and accelerates to a velocity v of 59.8 meters per second. So v, 59.8, the units are meters per second. And time, 6.5 seconds. And we are going to find the acceleration. The acceleration is unknown, but we know the units are meters over seconds to the second power. All right, so set up an equation for that situation. I'm going to give one a try here. T equals AV. So time is in seconds. Acceleration is in meters per second squared. And velocity is in meters per second. When we multiply those two together, we get meters squared on top, meters times meters, and we get s to the second power times s. That is s to the third power. Right, we have three of them being multiplied, so we get s to the third power. All right, well, those aren't even close to being equal, so that's definitely not the equation. All right, how about v equals a times t? Just switch it around a little bit. Okay, v, meters per second on the left. And on the right, we have acceleration, meters per second squared. And time is in seconds. All right, now seconds squared is just seconds times seconds. I'm going to write it like that. You can write it either way. And now we've got a seconds on top and a seconds on the bottom. That means one of those, not both of them, just one, always cancel in pairs. Those are going to cancel. What do we have left? Meters per second. So that matches, and that's a valid equation. V equals AT. Now we can use that to solve. Plug in what we know. A is unknown, that's going to stay a variable. 6.5 for T. And then on the left, we've got 59.8. Divide both sides by 6.5, and we get an acceleration of 9.2, and the units on acceleration are meters per second squared. Now, number 5 is another example of a problem that may include a bunch of terms that you don't know. But you don't need to know what they mean. You just need to follow the units. And that's the beauty of this method. I recommend starting by writing down the units. Our mass, 235 grams. We've got heat capacity, which has a variable C, and that's 4.18. And the units on that, joules per gram degree Celsius. J for joules, G for gram, degree Celsius. And we're going to add heat energy, Q, $74,000, J for joules. And finally, we're going to set up and solve an equation to find the increase in temperature, T. So temperature is unknown, and that is degrees Celsius. All right, so there's all our units. We got grams, we got this wacky thing, joules, and degrees Celsius. All right, so when I'm going to set up an equation here, I'm going to use the same trick I used last time, which is I've got this unit here, which has a fraction, which has all the units in it. So I'm going to put that by itself on one side of the equation. Now, we just have to arrange the units on the other side so that they match this unit. Joules over grams times degrees Celsius. All right, well, joules is on top, and joules is Q. So that means Q has to go on top. And I've got grams on the bottom, and grams is the mass. So M is going to go on the bottom. And we've got degrees Celsius on the bottom, and that is T. And now we know our units match, because C is joules per gram degrees Celsius. And on the right, Q is G, Q is J, M is G, and T is degrees Celsius. So they match. So a lot of times, if you've got a complex unit like this, you can use this to set up the equation. Just copy this form. All right, so now we have our equation. C equals Q over MT. And now we can plug in so Q is 74,000. And C is 4.18. M is 235. And T is unknown. All right, so to solve this, kind of a tricky one without the swap trick, but let's go ahead and swap those. 235T equals 74,000 divided by 4.18. So I'm going to go ahead and divide both sides by 235. You can go ahead and divide that out and then divide. You get the same answer. And when we divide like this, 235 ends up in the denominator. So we get T equals 74,000 over 4.18 times 235. Right, that gives us 74,000 over 982.3. And we divide that out, we get 75.3 degrees Celsius. So the temperature of the water changes by 75.3 degrees Celsius. So derived units are units that are made up of combinations of other units. And we saw an example of this here. We made a unit called joules over grams degrees Celsius. And there's a lot of formulas that contain constants that have a unit that looks something like that, made up of a bunch of different units with mathematical operations. And we can actually figure out what the units are of those constants. So let's say in your turn number 5, we were not given the units of the heat capacity. Let's say we didn't know. We knew that it was 4.18. We didn't know what it was measured in. Well, we can actually figure out the units by setting up an equation and then solving for that quantity. So let's say I started with this equation here. Q equals M times CT. And I want to find out what the units are on C. Well, we can use the techniques we learned earlier in the class, solving literal equations, and we can start by solving this for C. So I can divide both sides by MT. Right, the M's cancel, the T's cancel, leaving just C on the right. So we get Q over MT equals C. And then we just fill in the units for these quantities. All right, going back to our list, Q was in joules, M grams, and T degrees Celsius. And now we know the units on the specific heat capacity. Joules divided by grams times degrees Celsius. And this is actually how the units for those constants are found. Your turn number 6. There's a famous equation from physics, Newton's second law of motion. F equals ma. Force equals mass times acceleration. And we're given that the mass is measured in kilograms and the acceleration is meters per second squared. Now F is the force, and the unit of force is called the Newton, after Isaac Newton. So what I'd like everybody to do is figure out what a Newton is. What does the Newton equal using only these base units like meters and seconds and things like that? All right, so what we're going to do is plug in the units for mass and acceleration, and that'll tell us what the units are for force. So mass is kilograms, and acceleration is meters per second squared. Now when we multiply anything by a fraction, multiply by the numerator. So that means the force is the kilograms on top, multiplied by meters, all over seconds squared. Which means that the unit called a Newton is a kilogram meter per second squared. Your turn number 7. An important formula from chemistry is the ideal gas equation. PV equals nRT. Pressure is given in atmospheres. V, the volume, is in liters. N is the number of molecules in moles, like the earlier example we saw. And T is the temperature in degrees Kelvin. We want to find the units of R, which is the ideal gas constant. All right, so we want the units of R. So just like last time, let's get R by itself by solving for R. So we divide by MT on this side and MT on this side. All right, M's cancel, T's cancel. So that gives us PV over NT equals R. All right, now we're going to plug in the units. So pressure, atmospheres. Volume, liters. N is in mole. And T is degrees Kelvin. So that makes the units for the ideal gas constant atmosphere times liters over moles times degrees Kelvin. So we get some pretty strange looking units out of some of these constants. But the constants take whatever units are required to make this equation true. Now, there are other versions of the ideal gas constant that have different units. It all depends on what everything is measured in. For example, you might measure the volume in square inches, or sorry, cubic inches. That'd be another way to measure volume. And if you do that, you're going to get a different value for R numerically, and you'll get different units. And pressure, that can be measured in all sorts of different ways as well. Now this technique takes a little getting used to. If you're still unclear, don't give up. Stay with it. And I guarantee you, if you master this, it will take your math skills to the next level. This is an incredibly powerful technique that not only are we able to set up equations, we're able to see exactly why equations are set up the way they are. And it just leads to a much deeper understanding of the equation we use. That's it for today.